The last couple of things we need to talk about, which are really important for today's learning activity, are some of the more evidences for plate tectonics. And paleomagnetism is going to be looking at the magnetic pole structure of the Earth over a long period of time. You probably know that our magnetic pole roughly aligns with the geographic North Pole right now. I think it's just under 60 miles off from the actual, what we think of as North Pole and the magnetic North Pole. But this paleomagnetism was probably, for some scientists, the most persuasive part of plate tectonics. When magma solidifies into rock, the iron in the rock will actually, and the magnetite will align themselves with the direction of magnetic force. So your magnetite is still liquid at 585 degrees Celsius, which is what is the coolest this magma is going to be. And the magnetite is going to line up as it cools with the North Pole. And you can then figure out which direction that rock said was north. They stay frozen in place in that position once the rock solidifies. You can track these changes. We've been able to track paleomagnetic records to look at how the pole has changed its location over time. We call that movement of the pole changing polar wandering. And we can then average information from thousands of years to get a good idea of where the actual magnetic pole is. If the magnetic pole had remained stationary, what do you think that might have meant? If your magnetic pole is stationary and your continents are moving around, then you're going to see changes between the locations of the continents and maybe some changes in the seafloor if things are moving. If things are not moving, everything is always going to be lined up in the same direction, won't it? So movement is going to reflect the magnetic pole, provided it stays stationary, which it generally should. We use polar wandering for North America and Eurasia to actually line up the polar wandering of the magnetic rocks that are formed, of the granite and basalt rocks that are formed on the continents. And we can see that at a certain point they were together, overlapping, so they were like lined up. But we can also look at this in a very, I think, a much more persuasive way. And this is looking at the bottom of the ocean floor. As we get those spreading areas, each one, as it solidifies, is going to point north or south, well, north and south, dealing with the magnetic records. And we've been able to discover that there are time periods of normal and reverse polarity. Normal polarity is generally with the North Pole being at the North Pole. Reverse polarity is when the magnetic North Pole is near the South Pole. We do know that the Earth's magnetic field can reverse. The magnetic time scale is usually about, it's been the same for the last 4 million years. And we've discovered that there can be short, 1 million year time periods of reversals. And those reversals are usually quite short. Here they're showing the reversals in white with red marking normal polarity. And using that white and red color, you can actually map the seafloor spreading rates and figure out where the different rocks are and use that as a matching to see how things might have been spreading. Because it's nice when it's like that one picture there with the nice clear like layer stripes. But because things aren't always moving opposite of each other, you can see that there can be what look like turns in the polarities when it's really because of how the continents were moving and how those ocean ridges were being able to form and produce new oceanic plate. The way that we're able to detect these changes is by taking a magnetometer and suspending it from a boat and driving the boat across the bottom of the seafloor, looking for information about the seafloor. If you were to, who's used a compass? It points to the magnetic north, correct? These rocks are similar to a compass in the way that they form. They're going to point magnetically north. So you can get the magnetic information from them from the magnetite and look at changes. The magnetometer is going to measure how something like a compass is going to react to what's in the rocks. I don't have a magnetite sample, unfortunately, but if we did, we could look at how exactly that works. And over time, you'll see that the switches in polarity lead to changes of the different north or south pointing of the rocks, which is represented here by red and white. And that is it. There are portions of this chapter I did not cover. We're not going to cover them. Some of them, a number of reasons, but one is that a few of them are things that are theories for which there's no correct answer at the moment. And instead, we're going to make glaciers because that's way more fun. So that was all for this.